Okay. So last Thursday, that we mentioned two conditions under which the expectation of a series sum is equal to the series sum of the expectation of the random variables in the sequence. Okay, and so we would like to work out an example. Okay, so so x is a non-negative random variable, and specifically non-negative and integer valued. Okay, so right. So now for each integer, I greater than or equal to 0, we define xi equal to, so to be 1 if x of omega is greater than or equal to I, and 0 if x of omega is less than I. Okay. So xi is an indicator of the event. So basically, so you can say that x of I is the indicator of the event that x is greater than or equal to I. Okay. Okay. So you can think about that. This is the indicator, right? So this indicator is equal to 1 when this event occurs. That means that the value of this non-negative integer value random variable is greater than or equal to I. Okay. Of course, if I equal to 0, then x sub 0 is equal to 1, right? Because every value of this non-negative integer value random variable always greater than or equal to 0. Okay, so that is the special case. Oh, and okay, but maybe I think it's too big. So okay. Let's see. Maybe this maybe we don't need to use. Well, okay. So let me check. Okay. We would like to see I equal to 1 to infinity. So, okay. Let me check. Yeah, sorry. So it is not necessary to to use I equal to 0. All right. So we just need for each I greater than or equal to 1 that the x sub I is just indicator that the same, but we just need only I greater than or equal to 1. Okay, so when we look at the sum here, right, and when we look at the sum, okay, you can see that this is equal to I from 1 to x sub omega over x sub I plus summation I from x sub x of omega plus 1 to infinity. Okay, so we split this series sum into two sums. One is the partial sum. The other is also the tail of the series sum. Okay, and we cut to x of omega here. Okay, now the meaning of this one is that if x of omega is 0, if the omega is 0, it means that the sum is empty sum. Okay, so that this is empty. Okay, and so this is I from 1 to infinity, the same. Okay, as this one. Okay. Good. So this applies to every value, including the 0 value. Okay, so when we interpret that, if I from 1 to 0, that means that this sum is an empty sum by convention. Okay. All right. Now, so we can see that for x of omega, so if x of omega is positive, then the sum we can see that for all I from 1 up to this value, the x of I is equal to 1. Okay. Okay, so that is equal to summation I from 1 to x of omega, and this is 1 plus summation. But if I is greater than x omega, okay, so here is I is greater than x omega, right? The value is 0 by definition. Okay, and so how many ones we in this sum? How many terms in this sum? Well, we have x of omega terms, so this is x omega. Okay, and this is true for all omega in the sample space. Okay. Is that okay? So first of all, we prove that the series sum of these indicators is actually equal to the random variable of x itself. Okay? So now, since all x of I are non-negative, so we have that the expectation of x, so this is the expectation of the series sum of x of I. Okay? So now the expectation of the series sum becomes to the serious sum of the expectation of each x sub I. Okay. But what? This is indicator, right? As we know, this is indicator that x is greater than equal to I. Okay. So this indicator of this event, and the expectation is actually the probability that the x is greater than equal to I. Okay. So we prove the formula we have before that if when x is a non-negative integer value, the random variable, its expectation is the series sum of the probability of those events. Okay, for I from 1 to infinity. Okay. Any questions? Okay. So that I think the critical point is here to prove that this is series sum converge to the random variable x itself. Okay. All right. So now we move on to next section. Okay. So we will discuss a special situation, and which has many applications. Okay. Okay. So let's we have a number of events. So we have in here we have n events. So that okay, so we have A1, A2 up to AN. They are events of interest in the sigma algebra. And for each AI, we associate with an indicator. So the indicator, okay, function of the event AI, i.e., as we know, II omega is defined to be 1 if omega is in AI, and 0 if the outcome is not in AI. Okay. All right. So that's all right, and we let x equal to the sum of these indicators. So what is that? So this sum is the number of this event, right, that occur. Okay, so so for certain outcome omega, some of the indicator is 1, but some is 0. If the indicator is 1, means that the outcome is in corresponding event. So that means that the corresponding event AI S sub I occurs. Okay, and so X record the number, all right, of these events that occur. Okay, so for different outcome omega, so when we observe a different outcome, that means that the different number of this event that occurs. Okay, and the expectation, all right, of this number of events to occur becomes to okay. So the first moment would be the expectation of the indicator. That is from the linearity of expectation, right? As we know, if the linear combination involve the non-negative random variables and the coefficients are non-negative, okay, then the then this linear combination has expectation. Maybe infinite, but anyway, has expectation. So X must has expectation, and it's become to a sum of the expectation of each indicator. And as we know, because II is the indicator of event AI, so the expectation of II is the probability of this event, as we know already, right? Okay, so the expectation of X is just the summation of the probability of this event. Okay, so that's simple. But our purpose is to find the moment. So this is just the first moment, right? But we want to find the second moment, the third moment, fourth moment, etc. Okay, so we want to find any moment of X. Okay, so now the number of pairs, okay, of events that occur. All right, so the pairs, okay, it's this combinatorial number. Okay. So this is actually this number, right? Of course, it's a random variable. Why? Because it depends on the outcome omega. Okay, so if for certain outcome omega, X omega is 3. All right, so we have 3 possible events. Right, 3 events, 3 out of the n event occur, and so 3 events can have 3 possible pairs, right? Pairwise. Okay, so this is depends on. So it's a random variable, and and we know. So which is okay, so now which is equal to the summation II, ij. And a pair of events occur. Means that the product, for example, event AI and event AJ occur simultaneously, okay? If and only if the product of these two indicators is equal to 1. Okay? And so we check all possible pair. Okay. So we have this identity. Okay, in terms of the indicator. So that is from the pairing. Okay. Okay. So this number is equal to this one. Okay. If this is hard to understand, you may use, okay, this one is equal to summation indicator I of omega indicator of j of omega. Okay, so that is the same. So this is sum. This is sum actually. How many terms do we have in this sum? Well, we have in here we have n select 2, right? So this sum has n select 2 terms. Actually, so this is n in here, okay? So there are not many terms. And a term is equal to 1. Because the value of the term can be 0 or 1, right? And it is equal to 1 if and only if event AI and event AJ occur simultaneously, right? Together. So and if either one does not occur, then this product is equal to 0. So that this summation is just the number of pairs of events that occur if a certain outcome is observed. Okay? And this is exactly this number. Because this is the total number of events that occur when we observe omega. And so they are this number of pairs of events to occur simultaneously. Okay? Any questions? So there are two different ways to think about the same number. Okay? Okay, and so the expectation of x is equal to the expectation of this sum okay, and by linearity of the expectation. So this is EIJ. But a quiz, yeah, I think so. Yes, a quiz. This is actually so this is actually expected. So the product, the indicator, the product is the indicator of AI intersect AJ. Right? Remember that? The indicator of AI intersect AJ is equal to indicator of AI times indicator of AJ. Okay. But in our definition, this is actually like this the I sub I is actually the indicator is with our previous notation. II is actually indicator of AI. Okay, the same. Okay, and so this is summation. The probability of AI intersect AJ. And here, this is expectation of x minus 1 divided by 2. So that this is 1/2 of expectation x squared minus expectation of x. Okay. Maybe I will write here. Again, by linearity, right? So that the second moment of x is equal to the first moment plus 2, when we move to here, times the summation of this sum. Okay, so that this is the second moment. All right, so once, because the expectation, the first moment has been found here, okay. So now we have that, and this can be, so we can have okay. Now in general, the number all right, of distinct subset of K events that all occur is okay. So it's X and K. Okay. So if you observe an outcome omega, and so there are that many events out of the n event to occur, and so that you want to find the number of distinct subsets of K events. So from that many events, you select K subset. Okay, and so this is the total number of distinct subsets of K events from that many events to occur. And this number is actually can be computed. I1 omega, I2 omega, Ik omega. And the summation is that I1 less than I2, up to less than ik and less than equal to n. Okay. And so in here they are n choose k terms. Okay, so they are n choose k terms, right? And in each term, okay, you do the product. Okay, and as we know, we observe that the I1 times I2 times ik, this is actually the indicator of A, I1, indicator of A, I2, indicator of A, ik, okay, product. And in our midterm number 2, I think so, right? Midterm number 2, the first problem, you know this is the indicator of the A, I1 intersects A, I2 intersect A, ik. Is that correct? Okay, so that this product, the product of this indicator is actually the indicator of the intersection of A sub I1, A sub I2 up to A sub ik. Okay, and so this indicator equal to 1 means that this k events occur simultaneously. Okay, simultaneously. All right. And so that that would be the right hand side is the possible distinct subset of k events that all occur. Okay. So this established the identity here. Okay, and so that the expectation of this quantity, this is a function of random variable x, right? It's a function of random variable x. This is, it becomes to the sum of 1, I2, ik, and the expectation of I sub I1 times I sub I2 times up to I sub ik. Okay, and this is equal to ik. And because the product of this indicator is equal to the indicator of the intersection of this event, so this is probability of A, I1 intersect A, I2 intersect intersect A, ik. Okay, and you see that this one, this combinatorial number, xx times x minus 1 up to x minus k plus 1 divided by the factorial of k. So this is a polynomial function of x of degree k, right? Of degree k. because they are k factors, linear factors of x. And so when you multiply them out, it's a polynomial function of x of degree k. Okay? And so if we know the moment, the first moment, the second moment up to the k-1 moment, then we can compute the kth moment of x, okay, from this identity. Okay. So that's to find the moment x to the k, for k from 1 to up to n, up to m. Okay. We solve the system of m linear equations. With k. Okay, so this becomes to each one is a linear equation of the kth moment. Okay, each one is kth moment. And so that you can use any package, okay, which can deal with symmetry. Okay, like for example, like MATLAB is a good choice. Okay. Okay. Any questions? So maybe we can take an example to illustrate how to use that. All right, I think you encounter this match problem many times. Okay, so the problem is that each of n people selects height from a pool of their n heads. Okay. Maybe I use guessed. Maybe I use guest. So if there is a party, this party invite n guests, and each guest wear a hat to the party, and so they will put their hat into a pool before entering the party, and when they leave the party, then they should select one hat from the pool. And then the matching problem is that so X is the number okay, so X is the number of guests, right, who select their own heads. Right, so this is a standard matching problem, right? And in that problem, we know that the sigma. So the sum space is the set of all n factorial permutations. Okay? So for example, like oh, that is terrible, right? Okay, and so for this example, the number of match for this, so maybe I use omega, okay, the outcome. So for this outcome, the number of match is 2. Okay. All right, and there are some, I believe you have some experience in dealing with this match problem. So that let AI, the event, okay, that guest I select, right, select his or her head. Okay, so AI is the event that for guest number I, this guest will select the correct head. All right, and so that okay, and we know x of omega is the summation of indicator of S of I from I to n. Okay. because AI is the event that the ith person has a match. So the sum of the indicator give us the number of matches. Okay, so this is the typical application with us, right? And so to apply the formula, we have to find the non-homogeneous term, the constant term here in this system linear equations. Okay, because the left-hand side just linear combination of the case moment for k from 1 to m, right? The left-hand side there. Just like here, the left-hand side is that you can see is a linear combination of the second moment and the first moment. Okay. So similarly, from here you can see that it's a polynomial function of x, right? So it consists of the k's power of x, k minus 1's power of x, etc. Okay, and so the left-hand side is the linear combination of the case moment for k from 1 to m. And that is standard because when you do the expansion, the coefficient will be determined already. Okay? So the only thing you need to compute is this probability. Okay? All right, so we have to find the joint probability. Okay, so now for index, so now we want to find AI1 intersect AI2. Sometimes it's better we just use the common. Okay, and when you use the common by using the conditional probability I1, okay, so this joint probability is equal to the probability of AI1 times probability, conditional probability of AI2 given AI1 times probability of AI3 given AI1 and AI2 up to probability of times the conditional probability of AIK given AI1 up to AIK minus 1. And what is that? For this event, means that a person will select. So this person select first, right? So there are n heads there, and a person come here, come to the pool and select one of them. And the probability to have a match, okay? So that the AI1 means the I sub 1 person has a match. The probability is 1 over n. Okay? Okay? Now, how about this one? This one is that the condition on AI1. AI1 means that the person, the I sub 1 person has a match. Okay, so a head has been selected, right, by the right person. So there are only n minus 1 heads left in the pool, and the second person come to pick up a head, and we know that this person's head is still in the pool, so the probability is 1 over n minus 1. Okay, etc. For this one, person I1 select his or her head correctly. Person I2 also pick up his or her head correctly. So now 2 heads has been selected, right? So there are only -2 heads in the pool, and the third person come. And we know, given this condition, the third person's head still in the pool is one of the -2 heads. So after random pickup, the probability to have a map is 1 over n-2, etc. So up to here, we have n minus k minus 1. Okay? So it's very interesting that no matter what is the index, right? No matter what the index is, you can see that they will have the same joint probability. Okay? They have the same joint probability. Okay, and so that the expectation of x of k, x select k, this is equal to the sum. Okay, equal to the sum. But how many terms in this sum? Well, we have n pick up k. So we have, because here, I1, I sub k, and probability of A, I1, A, I2, A, IK, okay? And here we have n select k terms. So we have n select k terms. And each term has this number. So this one is n factorial and k factorial. Okay. This is actually is n factorial k factorial. Okay. And so here n factorial. Okay, so k factorial n minus k factorial. Let me see. Oh, sorry. n minus k factorial. I'm sorry. Okay. Okay. And here is n minus k factorial and factorial. So you cancel them. So this is 1 over the k factorial. Okay. Okay, so you know the sum. So this sum is 1 over k factorial. All right, and then you can compute to solve the system of m linear equations if you want to solve up to the mth moment. Okay. Okay. And for example, expectation of x, this is the expectation of x is 1, right? And this is, so k equal to 1, factorial, so this is 1. Right? So the first moment of x, the first moment of the number of match is equal to 1. Okay. No matter how many guesses you have, right? Very interesting. If you have 100 guests, the expectation 1. If you have 10,000 guests, the expectation also 1. Right? Very interesting. And the expectation of x squared, as we know, this is expectation of x plus 2 to the summation. So this is 2 factorial. Okay. And so this is 1 plus 1 is equal to 2. Okay. And so the variance of x, is expectation of s squared minus the square of the expectation. So this is 1, 2 minus 1 square. 2 minus 1 is 1. So the variance is also 1. And this number is also independent of the number of guests n. N may be very big, but the variance is also 1. The mean is also 1. Okay. All right. So it's a very efficient method to find the moment of the number of matches. Okay. Any questions? Okay. So if now and then we take a break for 5 minutes. Okay. All right. So so this is section application of the results about some basic properties of the expectation. Right? And so we will emphasize on the relation between two random variables. Okay. First of all, two random variables, x and y, okay, are called equal with probability 1. So we will say with probability 1, right, as a shorthand notation. If the event that x equal to y, this event, okay, has probability equal to 1. All right, so what is that? That is that we know x equal to y, this event. So don't forget it's a subset of the sample space such that the two functions x and y. Remember, a random variable is a function from the sample space to the set of all real numbers. Okay? So that if we collect all the outcome omega such that the x function and the y function has the same value at this outcome omega. All right? We put them together. So this is, right, it's called, and it is an event of interest because x and y, they are equal to each other. Okay? I'm sorry. Because they are random variables. Okay? So if you still have a question, say, to ask me why it's an event of interest. Okay? Then I will, if you ask me, then I will give you an answer, right here, by the following way. Okay, as an exercise of concept we learned before. So consider, okay? So consider a function which is equal to x minus y. Okay? So, which is a continuous function, right? On R2, right? It's continuous function. So that's, so maybe I ask why maybe, okay, I have to write down the question, right? So why this is subset? Because it's a subset, right, of the sample space. Okay, and the question is why this subset is an event of interest. Now you may ask me. Okay, so let me answer your question. Right. So the following way is that you consider such a continuous function. All right. So by proposition 6.3.d, that z defined to be, all right, is a random variable. Okay. Okay, so that's z equal to 0, which is z in this interval, right? Okay, it's in the sigma algebra, right? Because this is the requirement that for a function from the sample space to the set of real number to be a random variable, we ask that so z is in an interval, arbitrary interval, right? Must be an event of interest, and the 0, 0 is a special type of interval. Okay, so this is in F, but z equal to 0 means that x minus y equal to 0, and that means that x is equal to y. So this event, this subset is exactly z, the subset z equal to 0. Okay, and so this is in F. It's an event of interest. Yeah. Okay, so proposition 6.3.d is very useful. You see that I use that from time to time. Okay, so if you have a question, okay, if you have a question about some data processing of random variables, so x minus y is also a data processing, right, of x and y. Okay, and x equal to y is actually x minus y equal to 0, something like that. So you can. So it's an illustration for you to use proposition 6.3.d. Okay. Okay, so this one is an event of interest, and the probability of this event is equal to 1. Okay, so that means that for almost all outcome, that this value are equal. Okay, so we say, so sometimes when we say with probability 1, another way is almost surely. Okay, in other words, almost surely. Right, so almost surely is the same as with probability 1. Okay. Right. So this is a concept for equality of two random variables with probability 1. So in probability theory, if you say something with probability 1, okay, but that's in some informal situation, you can say that you can is surely. Whenever everything is almost surely, you can say surely. Okay, but I would like you to learn to use the phrase almost surely or with probability 1. All right, properly. Okay. A way to justify that x equal to y with probability 1, x to find an event omega 0 in the second algebra with probability of omega 0 equal to 1 such that x omega is equal to y omega for all omega in omega 0. Okay, so this is a very practical way. Very practical way. Okay. So you just find an event omega 0 such that this event omega 0 has probability 1. And then proof show that for all outcome in this omega 0, the two functions x and y are equal. Okay? Are equal. And if you need a proof, then that's fine. Since omega implies x, right, but by our requirement. So that means that omega is in the event. Okay. Okay. So that omega 0 is a subset of this event of interest. And so this means that probability omega 0 less than equal to probability of probability always upper bounded by 1. And this is lower bounded by 1. So that implies that what? Right? So for sure. Okay. And in many practical situations, this job is much more easier. Okay. But you have to observe to find out omega 0, okay, somewhere, okay, so omega 0 occur with probability 1. And show that for each outcome in omega 0, x and y are equal. Okay. Right. So that is a good strategy to do so. Okay, and also a random variable x is called no less than, I think that is not necessary. Okay, so maybe I don't need this concept. All right, so now I would like to give a proposition. Okay? And I try my best to give you a general version of this proposition. So let x and y be random variables with x greater than equal to y. Okay. So if we know that, so this means that okay. Actually, this inequality, the proposition is still valid when when this inequality occur with probability 1. Okay. But I want to let things simple, so I just say that x is greater than or equal to y. Surely means everywhere. Okay. Now there are two versions. If both x and y are non-negative, then the expectation of x is greater than or equal to the expectation of y. Okay. For non-negative random variables, expectation always exists, but may not be finite, but always exists. Okay. And so the expectation, so you can compare these two expectations. And the first conclusion is that because x is greater than or equal to y, all right, for every outcome, right? So the expectation is greater than or equal to the expectation of y. Simple, right? Second case is that x and y may be real value, the positive, negative, 0 arbitrary value. So if the expectation of x exists and finite, so when I write this one, we mean that expectation of x exists and finite. Okay? Then expectation of y is also exists and finite. Oh, not I can only say the expectation of y exists, but may not be finite. Yeah, may not be finite. Yes, but we still has this inequality. Okay, we still have this inequality. Okay, now first part says that both x and y are non-negative. Okay. Now, since x is greater than or equal to y, so we have x minus y is non-negative, right? So this implies that it's also non-negative. We proved that before, right? So this is non-negative. And also, since x is equal to x minus y plus y, so x is the sum of two non-negative random variables, right? Okay. So the expectation of x is equal to the expectation of x minus y plus the expectation of y. Okay. By the linearity of expectation. Okay. So in a remark on last Thursday, there are two versions of linearity, right? One is for non-negative random variables. The other is for general random variables with finite expectation. All right. So And this part, this one is already non-negative, so this is upper bounded by uy because this term is non-negative. Okay, so the proof is easy, right? Second, maybe I will say for non-negative random variables. Okay, so now second. Now to deal with arbitrary random variables, it's a little bit troubling. Okay, so we have to go back to our definition. Now, so first of all, we look at in here, how do we know that the expectation y exists? Well, expectation y exists if either its positive part has finite expectation or its negative part has finite expectation. Right? Existence means either the positive part of y has finite expectation or the negative part of y has finite expectation. Right? So we have to go back to our basic things. Now, first of all, first observe look at the positive part of y. The positive part of y for some outcome is positive. This if only if is y omega is positive, right? By definition. Okay? But as we know, x is greater than or equal to y, so this means that x omega greater than or equal to y omega and greater than 0. So that for this omega, this is equal to x plus omega, right? Because this is greater than 0. So x plus omega is greater than y plus omega. Okay. Right? So when y plus omega is greater than 0, then we have this inequality. And the other case is when this is equal to 0. Because the positive part is always non-negative. So there are only two cases, right? Either this is greater than 0. Okay? So we have to go to possibility, right? So for any outcome omega, either the positive part is positive or the positive part of y is 0. And when the positive part of omega is 0, then of course this is equal to, then for this omega, x plus omega is greater than or equal to y star omega. So for any omega in the sample space, we arrive into the same inequality. Right? So together, we know that x is greater than or equal to y for all. So i.e. x plus is greater than or equal to y plus. Right? Very interesting. So when x is greater than or equal to y, when x is greater than y, then the positive part of x as a random variable, right? The whole is greater than or equal to the positive part of y. Okay. So here. Now, next we have to compare their negative parts. And then you will have a surprise result. Surprising. Okay, so in here, okay, so for, again, we have two ways. Okay. If the negative part of x is a positive for some outcome, so that means that the x omega is less than 0, right? By definition of the negative part. And we know y omega is less than equal to 0, right? Because of here, x is greater than or equal to y. So we have that. And this means that, so now y omega is negative. So that means the positive part is the negative of this y omega will be greater than or equal to the negative of this omega. Okay, so this is minus. If you, so that means that minus y omega greater than or equal to minus x omega greater than 0, okay? And so this implies that y minus omega greater than or equal to x minus omega greater than 0, okay? So that is the first case. The second case, x minus omega equal to 0, implies that y minus omega will be greater than or equal to x minus omega, which is 0. Because y minus is a non-negative random variable. So together means that y minus omega is greater than or equal to x minus omega for all omega in the Sum space. I.e., y is greater than or equal to minus. Okay. So when x greater than or equal to y, then the negative part of y is greater than or equal to the negative part of x. Right? On the contrary to the positive part. Very interesting. And from here, we can see that so that by 1, the first when both are non-negative, when they are non-negative, right? We have this inequality. So that expectation of x bar is greater than or equal to the expectation of y plus by 1, right? And again, by 1, expectation of y minus greater than or equal to expectation of x minus. Okay. Okay. So this is what we have. Now, we further assume that expectation and note that expectation of x is finite if and only if expectation of the positive part is finite and the expectation of the negative part is finite. Right? So the assumption that expectation of x is finite means that both of them are finite. And from here, because the expectation of positive power of x is greater than the expectation of positive power of y, so that this implies the expectation of y plus is finite. Right? It's finite. Okay? Because the expectation always greater than 0, right? And from here, this implies that expectation of y exists. Okay? So we prove the first result. Expectation y exists. Okay, and lastly, maybe I use it here. Now, expectation of x is expectation of x plus minus expectation of x minus. Okay, by definition. And this is greater than or equal to the expectation of the positive power of y, right? So this is the lower bound of the, this is less than or equal to this one. And you subtract something bigger, so you keep the lower bound. So this is smaller than this one is bigger than this one. And it's possible that this term is infinite. Okay, it's possible this is infinite, but that's fine. Okay, and this is expectation of y. Okay, get the result. Okay, so you can see that even for this simple relation, to prove the general result, the implication here, okay, we still need to go back to our the primary definition at the beginning of the definition of expectation. Okay. Okay, and so proposition 7.4.b a random variable z has second moment equal to 0 if and only if z is equal to 0 with probability 1. Okay. So the proof. Now we go to this direction. So that the second moment of z is 0. Okay. Under this condition, we want to show z is equal to 0 with v1. Okay. Now, so we first show that the probability that z, the absolute value of z greater than 1 over n is equal to 0 for all n in the set of natural numbers. Okay. Okay. So we want to show that this is true. Okay. Now we prove that by contradiction. So suppose that there exists a positive integer n such that probability of this event, the absolute value of z greater than 1 over n is greater than 0. Suppose we have this situation occur. Now, since z square is greater than or equal to z square times the indicator of z square. All right? Now, z, this event, the absolute value of z is greater than 1 over n. Okay? This is equal to this square is greater than 1 over n square. Okay? So if you square the two sides, okay, so they are the same. So these two events, this event and this event are the same. Okay. All right, so this is 1 over n square times the indicator, right? And the indicator is either 1 or 0. So it's the lower bound, no problem, right? This is a lower bound. Okay? And when the indicator is 1, z square is greater than 1 over n square. So that means that it has an lower bound n square of indicator z square greater than 1 over n. Okay? Any questions? Let me explain it again. Because the indicator has value either 1 or 0. If it's 0, if the value is 0, then the product is 0. Okay? And so, I'm sorry, I forgot to put. In that case, then this is 0 too, right? So when the indicator has 0 value, then this is equal. But when the indicator has value 1, okay? In that case, z square is lower bounded by 1 over n square. So that z square, this is z square, is lower bounded by 1 over n square. So we can replace the z square by this one. Right, so okay, so we have this inequality. So now, so this is the this is non-negative random variable, and this is also non-negative random variable, and we have inequality, right? So by the previous proposition, so that expectation of z square, okay, will be greater than or equal to the expectation of the square indicator of z square greater than this one by proposition 7.4.A1. Okay, the first. And by linearity, this is n square, expectation of the indicator z square greater than, 1 over n square. Okay. But expectation of an indicator of an event is the probability that z square greater than 1 over n square. Okay. And here we know we have assumed, suppose that this is positive, so this is positive. So we prove that the second moment of z is positive, which is a contradiction. Okay? So this is a contradiction. To what? To our assumption here. The second moment is 0. Okay? So when we suppose that this event is positive, then the second moment becomes too positive, which is a contradiction. Okay. Okay, so now we know. So now we know that this is true for all n, for all non-negative integer, for all positive integer n here. Okay. All right. So now z greater than 1 over 1 contained in z greater than 1 contain half right up, and so it will up to what? Up to z not equal to 0. Okay? Not equal to 0. So we have a monotone increasing sequence of events, and the limit, their union is the event that, so this is equal to z not equal to 0. Okay? So that the probability that z not equal to 0, right, it's the probability that the limit n goes to infinity of the event z greater than 1 over n. Okay? So this event is the limit of this increasing sequence of events. And by the continuity of the probability measure, this is the probability that z greater than 1 over n by the continuity of p. Okay. But we have shown, so we have shown that this probability are all zeros. Okay. So the limit of 0 is 0. So probability of z not equal to 0 is 0. So this means that So our conclusion okay, so that probability of z equal to 0 is equal to 1 minus probability of z not equal to 0. And it's 1 minus 0. Okay, so that's 0 equal to z equal to 0 with probability 1. Okay. All right, so we have shown that if the second moment of z is 0, then z is equal to 0 with probability 1. Okay. Now the reverse direction. Suppose if assume z is 0 with probability 1. Okay. So now with probability z equal to 0 is equal to 1. So we have expectation of z square and so this is the z square probability z equal to 0, and this is 0. Okay. Okay, and so now we will prove an important result called Schwarz inequality. Okay. We proved Schwarz inequality for simple random variables before, and we will take the same strategy to show the general result. So suppose x, y are two random variables with finite second moment. Okay, i.e. expectation of x squared is finite, expectation of y squared is finite. Right? So we assume that then their product, okay? Then their product has finite expectation, okay? Not only exist, but also is finite, okay? And the square of this finite expectation is less than or equal to the product of their second moment. Okay. And where the equality holds. Okay? If and only if either y equal to alpha times x or x equal to beta times y with probability 1 for some constants alpha and beta. Okay, so that is a full version of Schwarz inequality. Okay, because it includes a necessary and sufficient condition that the equality holds. Okay, so it's very general that x and y are two random variables with finite second moments, so their second moments are finite. Okay, and in this case, then their product x times y has finite expectation. And this finite expectation, when you take the square, we are upper bounded by the product of their second moments. And the equality hold if and only if either y is equal to alpha times x or x is equal to beta times y. Okay, with probability 1. Okay, for some constants alpha and beta. Okay. So Schwarz inequality is a very important inequality in probability theory. And we are well prepared to prove it. Okay. First of all, if one of the second moment is 0, says okay, so if one of these two is 0, okay, maybe I will more specific. I just say, all right, if expectation of is 0, then we know x equal to 0 with probability 1 by proposition 7.4.a B, sorry, the previous result. Yes, okay. So if the second moment of x is 0, then x is 0. All right. Thus, x times y is equal to 0 with probability 1. And so that, right, the expectation, so that the 0 is the expectation of xy, right? So expectation of xy is 0. Okay, 0. So it has, in particular, it has finite expectation, of course. And this is less than equal to which is 0 times expectation of course. So the inequality set is true automatically. And the equality hold. So actually the equality holds, right? Maybe I will just say this is equal. Okay, it's already equal. And x is equal to 0 times y with probability 1. Okay, so the alpha is 0. Okay, oh, beta is 0. Okay, I'm sorry. So you find a beta which is 0. Okay. And similarly, if this is 0, then y is 0 with probability 1 by position 7.4.b. So that's xy is 0 with probability 1. So that 0 is equal to expectation of x times y is equal to ex square, second moment of y, second moment of x times 0. So you have equality, and y is equal to 0 times x with probability 1. Okay. So for two special cases, the proposition is true. Okay? All right, so we will assume, so assume that okay, or you may not use, you may say consider, all right, the case. Okay. Okay, and we let x bar to be x divided by the square root of its second moment, and y bar is y divided by the square root of its second moment. Okay. We are able to put the square root of second moment into a denominator because we consider them to be positive, okay? So we have that. Right, and so we take, now, so we have this inequality. Okay, so that if we take plus minus, right, of x bar, y bar here, and take the square, now we know that this would be non-negative. Would be non-negative. Okay. Okay, and so that if we factor out the square, we have the square of x bar plus the square of y bar will greater than equal to the plus minus 2 times x bar and y bar. Okay? So this means that x bar square plus y bar square greater than or equal to 2 times the square root, the absolute value of x bar and y bar. Okay. So they are even only condition. If you have trouble with this argument, because we look at x bar is a function, right? Y bar is also a function of omega. So this is the sum or difference of these two functions. But anyway, the sum or difference of these two functions are also real valued. So when you take the square, all right, so now this square, the function will be non-negative valued. Okay? And so the square of this function plus the square of this function will be greater than or equal to plus minus 2 times the product of these two functions. All right, and then you have this one. Okay. So they are functions. Okay. All right, and so now, so they are non-negative random variables. Non-negative random variables. So from here, so we have, this is implies that the expectation of so that 2 times the expectation of x bar, y bar, okay. This one is then equal to, oh, maybe I just say expectation of 2 times x bar, that's then equal to expectation of x squared. So this is from proposition 7.4.A1, right? For non-negative random variables. Okay. And by linearity, this okay, this one. And then you compute, because you plug into here, you find that this is okay. When you take the square, you square them, you get here. And this is expectation of x squared, expectation of bilinearity of expectation. One plus one equal to 2. Okay. Is that okay? So we have this one. Okay. Right, and you see here. So this is 2. All right. So you see, so that expectation of x this one is less than equal to 1. Okay. Oh. The 1 here. And we plug into there. So here we have square root of okay. So we plug into the definition of x bar and the bilinearity of expectation. So you can take out the constant, the coefficients here. So that you have expectation of xy is upper bounded by the square root of okay. Oh, I think I have something. Okay. Okay. Okay, and this is finite. So that expectation of xy is finite, exists and finite because its absolute value is finite. So that the expectation of xy is finite. Okay. And the since xy is less than equal to minus xy, so that expectation of xy is less than equal to expectation of xy, and this is less than equal to expectation of okay. So finally, you take the square, then you don't have, you have this. Okay. All right. And equality. Okay. So the equality holds. So you can go back to C. Equality holds if we have first of all that x plus minus y bar x expectation of okay. So the way to okay, maybe I would doing this argument would be faster than everything. Okay, so the way is to we have proof that the product x and y has finite expectation. Okay, great. So we have proved that. Okay. All right. So now, all right. We know ax minus by for all AB in R. Okay, so that now we look at arbitrary linear combination of x and y. And so this is a square expectation of x square minus 2ab. All right, we a square x square minus 2ab xy plus b square y square. Okay. Now we know x square has finite expectation, y square has finite expectation, and the xy has finite expectation, right? So they have finite, and so they are. So this is a linear combination of these three random variables: 1, 2, and 3. Okay? So by linearity of expectation, so we have that, so we can write down okay? So we can apply the linearity because we have proof that the product x and y has finite expectation. If we haven't proved the product has finite expectation, then we cannot use the linearity of expectation. Okay. All right. And now A, B can be arbitrary, right? So now we can do the perfect squaring. So A minus, here is expectation of xy and the expectation of x squared and the B okay, so the square root here, right? This side, okay. Oh, no, don't take the square root. Okay. And the plus expectation of x squared, and this is expectation of x squared, expectation of y squared, minus expectation of xy squared. Okay? This is by doing the perfect squaring. Okay? So you just take the factor out and give it this one. Okay, so this is good for all AB in R. This is good for all AB in R. All right. And look at, oh, sorry, this is squaring here. So now, this is non-negative. This is positive already, right? And this is non-negative. So this term is non-negative. And b squared is here. So if this one, if this term, so we can, for example, because A and B can be arbitrary. If the numerator if this one is non-negative, is negative here. Okay, so if this is a negative value there. Now you can later B. Okay, for example, you can let A equal to B times this number, right? So that this is 0. And the B can be arbitrary, so this becomes to negative. But as we know, at beginning, the lower bound is 0. Okay? So if this inequality to be true for all AB in R, the only you can have is that this numerator is greater than or equal to 0. It cannot be negative. Okay? Can you see that? Okay? Because you have 2 degrees of freedoms here. For every AB in R, this term must be greater than or equal to 0. So for example, you can always let A equal to B times this coefficient. So you can cancel them. Okay? And the B can be arbitrary, right? So now the degree of freedom becomes to only 1. B can be arbitrary. If the numerator here is negative, then this term will be negative. That is a contradiction. Okay? So the only thing, so this implies that EX squared times EY squared minus EXY squared must be greater than or equal to 0. Okay. So we must have otherwise, by setting A equal to B, and B not equal to 0, then we have 0 less than or equal to divided by this square. Okay, this one is less than 0. Okay, so when you choose A equal to this and B not equal to 0, then this term become to negative. So you have 0 less than 0, okay, and a contradiction. So that's expectation of xy square would be less than or equal to, so we have the Schwarzer inequality, okay, and the equality holds. All right, so now look at equality holds. Equality holds when the equality here okay, if and only if AX plus minus AX minus BY equal to 0 with if and only if so if the equality holds here, if the equality holds, then this term is 0, okay? This term is 0, and A and B is 0, okay? So so only here the equality, if this is the equality, okay. It's if only if AX minus BY equal to 0 with probability 1, maybe I will say expectation of it's equal to 0. And if and only if ax minus by equal to 0 with probability 1 by proposition 7.4 point B. Okay. Okay. So this is if only if x is equal to a of by or y equal to b of ay, b of ax. Okay. With probability 1. Okay. So if this is 0, okay. Yeah, I think it's too short. Maybe so I have to say okay. I think I have to separate because it's, if the equality holds, then expectation of ax minus by square is 0 for a equal to and the b equal to 1. Yeah. Okay. So now if the numerator is 0, okay, so this is 0, right? And if we let a equal to this one, so b can be arbitrary. So we assign b equal to 1. Okay, so we can assign b equal to 1, and a is just this quantity. Then this is 0. Okay, so it's equal to 0 because this is greater than equal to 0, and this is 0. So that's this expectation is 0. Yep. Okay. Okay. So we have that situation here. And from here, so this is implies that a is minus by. So we can solve. The y becomes to e of xy given e x squared and x. Okay? So we solve this with probability 1. by proposition 7.4.b. Okay. Yep. Maybe one more steps. The ax minus by equal to 0 with probability 1 by proposition for a equal to and b equal to 1. Okay, so that this implies that y equal to okay, so we find this is beta, right? Oh, alpha. Okay, so alpha, y equal to alpha. Yep. In this case, okay. So we show that if the equality holds, then we know y is a factor, is scalar product of x with probability 1. And conversely, if either y equal to alpha x or x equal to beta y with probability 1, then when we compute square, now this is the expectation of, for example, for this one, so this is alpha x squared. Okay, and so we have alpha square, and you can split square alpha square e. Okay, because y is alpha square. Y is alpha times x. Okay, so you can absorb them inside. For this case, and comes to beta y square. So it's beta square. So this is beta square times so we show the equality directly. Okay, so which shows that the equality holds. Okay, so this complete proof. I'm sorry, it's a long proof. Okay. So so we have to, before we can show the inequality, the Schwarz inequality, we have to show the product has finite expectation. Okay. Right. So we take some parts to show that it's indeed has finite expectation here. Okay. By showing that that its absolute value of xy is upper bounded by this quantity. Okay. All right, and then we derive the Schwarz inequality in a standard way. So we take the linear combination of x and y for arbitrary a and b. Okay. And so this inequality is true for arbitrary a and b. And for that, this numerator should be non-negative. Okay, otherwise we will have a contradiction. Okay. And then the last thing is that if this is 0, if the Schwarz inequality has equality, okay, and then we show, in this case, we show that with a and b select properly. So if we select b equal to 1 and a is equal to this quantity, then with that a and b, this expectation is equal to 0. Okay, because the lower bound is 0 and actually this is 0, right? So in that case that because this is 0, so by proposition 7.4.b, this difference is 0 with probability 1. And with a is this number, b is equal to 1. So when we plug into here, we find that y is the scalar multiplication of the random variable x with probability 1. Okay, so this direction is true. Okay, because this is all 1, right? Either 1. And the backward direction, when y is the scalar multiplication of x, or x is the scalar multiplication of y with probability 1, then we just compute their the expectation of their product first. Okay, and plug into this case or that case here, right? And by linearity of expectation, so we have this one. Okay, and then we go back to here to find that this is the product of their second moment, and show that the equality holds. Okay, so now we establish the if and only if condition. Okay, so that is the Schwarz inequality. Okay, in its a general version. All right, so I think I stop here. Okay. So we have proved quite a few important propositions which can be used in many situations. They are very basic, okay, and so that we take some time to give a full proof. Okay, so I stop here.